Alright, welcome back to fractional calculus class. My name is Godobe. So today we continue to check the definitions of Riemann Liouville fractional integral. So we continue where we stopped last week. Last week we checked Riemann integral, whereby we have integral of alpha, function of x equals to lim m tends to infinity, h raised to the power alpha, and summation k equals to 0 to n, gamma alpha plus k over gamma k factorial gamma alpha, and then a function of x minus k h, whereby our m is given an x minus a over h and our a have to be less than x. So let's check what if our alpha is equals to 1. What will be our result? So let's substitute alpha equals to 1 in this our Riemann integral. So we are going to have integral 1 ax of f equals to lim m tends to infinity, h is power 1, summation k equals to 0 to n, and gamma 1 plus k over k factorial and gamma 1 f of x minus kh. And we know that our gamma 1 plus k is given as k factorial, and gamma 1 is given as 0 factorial, which is equals to 1. So let's substitute that into the equation. We're going to have lim m tends to infinity h, and then summation k equals to 0 to n. So we have k factorial over k factorial, and then 1 and 1, that is gamma out, that's 1. So we have x minus kh. So this actually cancel this. So we'll be left with lim m tends to infinity, summation k equals to 0 to n, f of x minus kh equals to h. Okay. So in order to take this to integral form, we have to let kh equals to t, and then our h equals to dt. So you can actually prove that using your normal xy coordinates. This is your t now, and this is your y. So if we have something from here to here, so the difference is taken as h, which represents your dt. Okay, so going by that, we are going to have lim m tends to infinity, summation k equals to 0 to n, f of x minus t, because our kh is now t and our h now dt. Alright, so with this now we can now select, once we write this using our integral properly. So we are going to have, let's bring in our limit. We have our slope m, which equals to x minus a over h. So we can actually include minus 0 here. So why this is our b minus a, b minus a, so our a equals to 0 and our b equals to x minus a. So we plug that in here. So we are going to have integral 0 to x minus a. Then we have f of x minus t dt. This integral when alpha equals to 1. Alright, so let's implement substitution method by saying let u equals to x minus t. That means our du and dt, that will be minus 1. Then with that we can have our dt equals to minus du. And also, since we are transforming it to u, then we have to do something with our limits, and this is the value of t. So let's first of all take at t equals to 0, then our u equals to x minus t, which is 0, then our u equals to 0. Also the upper limit, that is at c equals to x minus a, we have u equals to x minus 2, which is x minus a. Then we have our u equals to a. So substituting these those terms, we are going to have our integral when alpha equals to 1 to be 0. So when our t equals to 0, we have our u equals to x, pardon. So we have x equals to x to a f of u minus du. Alright, because of that negative, we are going to have integral a x instead of x a now. So it turns upside down because of that negative du. So when we have our alpha equals to 1, then we have this result. So let me write it somewhere here, and then we'll continue when our alpha, let's try to check when our alpha is equals to 2 before we make a general conclusion. When alpha equals to 1, we have our integral 1 f of x to be integral a to x f of u du. So then I come back here and find out when our alpha equals to 2. So let me delete all this. So then I now check when alpha, machine the pen, when alpha equals to 2, that's what we are going to have. So we have integral 2 a x f. So we are substituting alpha equals to 2 into the equation. We have h square summation k equals to 0 to n and gamma 2 plus k, okay, k factorial, and then gamma 2 f of x minus kh. So putting in our gamma and taking it to factorial, so we are going to have, that will be 1 plus k factorial, 1 plus k factorial, we have k factorial, and we know our gamma 2, that will be 1 factorial f of x minus kh. So with this now, we have lim m tends to infinity a square summation k equals to 0 to n. Then we can extend this step for 1 plus k, then k factorial over k factorial. 1 factorial is 1 over f x minus kh. Then this cancel this. Done with that, we are going to have lim m tends to infinity summation a square n equal to 0 1 plus k f of x minus kh. So I'm going to go a step forward. Moving a step forward, as k is equals to 1 is going to affect this one, and that will now become, that means we are going to have k here, that is lim m tends to infinity a square summation k equals to 0 to n. Oh, sorry, we are now going to have k equals to 1, then m plus 1, then this will now turns to k f of x minus kh.